In this work, we present ZeroCAP, a zero-shot multi-robot context-aware pattern formation framework via large language models. Imagine a scenario where we need to surround an incorrectly parked car with robots based on user instructions. This might seem simple, but it poses some key challenges. The first is understanding complex natural language instructions. The second is identifying objects despite ambiguity in these natural language instructions, such as identifying the incorrectly parked car. The next challenge is about understanding spatial relationships, which would allow the robots to be placed in the context of the car and the user instruction. All of these challenges must be applicable in a zero-shot setting, which would require no pre-training, even if the environments or the objects are generalized to different scenarios. With ZeroCAP, we expect our system to result in the following output, where the robot cones are essentially aligned around the corners of the object. The entire process for ZeroCAP starts off with two user inputs. The first is an image of the environment, and the second is the instruction, which are passed to a vision language model that identifies the context of the task. Now, once the context and the object are identified, it goes to stage 2, where we segment the object and encode it in an underlying shape description of vertices and edges. In stage 3, an LLM-based pattern former is used, which takes three key inputs: the number of robots, the shape description of the object, and the pattern formation instruction. It then provides coordinates for the robots to be deployed in the real-world setting. ZeroCAP enables three types of pattern formations. The first is general, where robots arrange themselves around an object. The second is infill pattern formations, where robots occupy a region's interior. And finally, we have caging pattern formations, where robots form a boundary around an object. The results demonstrate that vision language models alone are insufficient for context-aware pattern formation without improved spatial reasoning. In the case of the RL baseline, RL struggled with general and infill tasks, but excelled in caging tasks due to consistent goal of forming barriers. This shows RL's effectiveness in structured tasks, but its limitations with more nuanced instructions. In the case of ZeroCAP using GPT-4 outperformed all the other methods, and general pattern formations was the most challenging due to the abstract instructions. Experiments were carried out across all the three task types and across different environmental settings as well. Some environments show only a single object, where there's only one object that is in context of the pattern. Some environments have multiple objects, with some objects posing as distractors. And finally, we have a hidden object environment where the instruction provides ambiguity and the object must be reasoned and identified by the vision language model. To summarize, ZeroCAP moves beyond traditional approaches by integrating LLMs for natural language-based pattern formations. We further validated the framework in both simulations and real-world environments. Lastly, we effectively solved the limitations that VLM have when faced with spatial tasks.